Welcome everybody to my talk, which is about an ongoing project. The purpose of this short presentation is to give a brief summary of results I already obtained, and at the end I will also state some open questions. The motivation of the project was to consider a classical problem from non-parametric statistics, namely spectral density estimation from a novel point of view, which is given through the constraint that only data that are in some sense anonymized can be observed. In this talk, I will work in the particular framework of local differential privacy. Let us consider the setup. We have a stationary time series with autocovariance function gamma, and our objective is to estimate the corresponding spectral density f from a finite snippet of the time series of length n, but under privacy constraints. Before I introduce the precise framework of privacy we're going to consider in this talk, I will recap results obtained in the classical case of non-private observations. Estimation in the non-private setup is usually based on the centered periodogram, and it is well known that the periodogram itself does not yield a consistent estimator of the spectral density, but it has to be smoothed in advance. One possibility here is to project the periodogram to a finite dimensional model that is given by the linear span of some finite set of orthogonal basis functions. In this situation, one can derive an upper risk bound that can be decomposed into an approximation error and a stochastic error. If one does this, for instance, for the classical basis consisting of trigonometric basis functions, one gets the classical non-parametric rate stated here, where S denotes the smoothness index of the Sobolev ellipsoid. This rate optimal estimator, however, depends on the appropriate choice of the underlying model, that is, in our case, the number of basis functions used in the definition of the estimator. However, one can also obtain an oracle inequality of the following form, where the statistician selects a model from a finite set of candidate models using a penalized contrast criterion. Depending on the specific choice of the penalty used in the procedure, one obtains a completely data-driven estimator that is either rate optimal or at least attains the optimal rate up to logarithmic factors. All of these results can be found in the nice paper of Fabien Comte. This is the situation in the classical world, where one does not have access to the original time series data. And now we come to the situation under local differential privacy. The concept of local differential privacy originally comes from the computer science community and has been made popular in statistics in the last decade, starting with the seminal paper of Ducci, Jordan, and Wainwright. Roughly speaking, a privacy mechanism is a Markov kernel that randomly generates a privatized output Zi given the private data Xi. The quantification of the privacy is given by a condition on the likelihood quotient of the Markov kernel. This condition can also be interpreted as a bound on the disclosure risk of the original data. The parameter alpha here is the privacy parameter, and the extreme cases alpha equal to 0 and alpha equal to infinity correspond to scenarios with perfect or no privacy, respectively. We now come to a potential anonymization strategy in our time series framework. We assume that each observation Xi belongs to a different data holder who wants to publish only a private surrogate of this observation. This anonymization proceeds in two steps. First, we truncate the observation by a threshold tau n that is allowed to depend on the sample size. And then in a second step, we add appropriately scaled Laplace noise to this truncated version of the data. Now one can show by an easy calculation that the Zi defined this way satisfy the constraint of the alpha local differential privacy. The obvious question is now how one can estimate the spectral density from these anonymized data. The classical periodogram is not available anymore, but we can replace it with a privatized periodogram where we have just replaced the xi in the definition of the periodogram with the privatized data zi. We further modify this privatized version of the periodogram by subtracting the constant term, which is caused by the Laplace noise used in the anonymization procedure. Having done this, one can proceed as in the non-private case and project the resulting I hat n on a finite dimensional model. The resulting upper risk bound has a similar structure as the one in the non-private case, but there are some additional terms containing the privacy parameter alpha and also the threshold parameter tau n. However, in the case of Sobolev ellipses, one can at least show that up to potential logarithmic factors, the same rate as in the non-private setup can be realized. This is somehow surprising since in many situations, like for example, non-parametric density estimation, a deterioration of the rate under local differential privacy cannot be avoided. Also, as in the non-private case, one can also define a penalized contrast estimator. But now the penalty can also depend on the privacy parameter alpha, and one obtains a similar oracle inequality as in the non-private case. In order to obtain such an oracle inequality for the private case, one can rely on recent concentration inequalities for quadratic forms in terms of sub-exponential random variables. In order to illustrate the approach, I show you some simulation results, where I considered time series snippets of length 10K and 20K and privacy parameters equal to 2.5 and infinity. In a Monte Carlo study, I repeated the simulations for each setup 100 times and calculated the pointwise mean of the estimators. The pointwise mean of the estimators is given in the plots by the red solid line. I also calculated the upper and lower 5% quantile, which is given by the red dotted line in the plots. The true spectral density is indicated by the black dashed line. The numerical results indicate that local differential privacy is quite a strong restriction, and one needs much more observations in order to obtain the same level of accuracy as for the case of non-private observations. I come to my conclusion. First, non-parametric spectral density estimation is possible also under local differential privacy, and one can obtain nearly the same rate as in the non-private setup. Moreover, oracle inequalities as in the non-private setup can be proved. The main open question that I currently work on concerns the exact dependence of the convergence rates on the privacy parameter. I thank you very much for listening to my talk.